So our aim today with this screencast, guys, is to look at the concepts of circular motion in a vertical plane. The big difference, of course, is that now we have to consider gravity. If we've swung things around in a horizontal circle, gravity is perpendicular to our motion, so it doesn't have any effect on our acceleration towards the center of the circle. The second scenario we looked at was circular motion at an angle, like bank tracks, and that's where our formula tan theta is v squared on rg comes from. We need to consider components of our weight force. Now, of course, gravity or your weight force is acting in the direction of motion. So the sort of scenarios we'll look at are things like like a bucket, or sometimes you come across things like a billy tea being swung in a vertical circle around a campfire. Obviously, we've got things like your roller coasters, aeroplanes going into or pulling out of a dive, because that's vertical circular motion. We've got also things like anything going over a bump. So we're going to explore the concept of weightlessness as well. Okay, we start with our basic truth, our go-to, and that's this statement here. To keep moving in a circle, the net force on the object or the person needs to satisfy that centripetal force requirement, and we've talked about that a few times. So the net force, the resultant of the reaction force and their weight. So, now if we go back to our diagram, your weight force is easy. It's always acting downwards. So it doesn't matter where they are. If they're over here, it's acting downwards. If they're down the bottom, it's acting downwards. Now, in these circumstances, it's the reaction force that changes. If you consider the person sitting in the seat, it's the reaction force of the seat on their bum or their body. Similarly, down the bottom, it's the reaction force of their seat on them. If you think about the roller coaster itself, it's the reaction force of the track on the carts. So it does depend upon which part of the system you're thinking about. A lot of the time we'll think about the reaction force of the cart or the seat on the actual person, or like the seat of an aeroplane on the pilot, for example. Okay? All right, let's not get ahead of ourselves. So once again, we start with a basic truth that if things are going to move in a circle, your net force needs to be towards the center of the circle and supply that centripetal force requirement. Where does that mv squared on r come from? It's the net or resultant of your reaction force and W for weight. All right. That's inescapable. All we're going to do now is recognize that we're just going to tweak that formula. That's all we're going to do. We need to recognize that if it's going to be a constant circular motion, your centripetal force needs to remain constant. Your weight force, unless you magically shift to another planet, is going to remain constant and downwards. So the thing that is going to change is the reaction force on you or on the roller coaster, whatever it may be. And I think the next statement will just repeat what I've said. Let's go through it. If the speed of the circular motion remains constant, then the magnitude of the centripetal force required is also going to be constant, isn't it? Yeah? Notice it said magnitude. The direction's going to change because it's always towards the center of the circle, but the magnitude remains constant. So the weight force, W, is also constant and downwards. So the only force that will change as you move around the loop is the only one that's left. Guys in the class here, help me out. Exactly. Okay. Is your reaction force. Like I said, whether that's the reaction force of the seat on the pilot or, a seat on your bum or your body or, the wings, the lift provided by the wings on a plane, whatever. Okay. So if we rearrange this formula, here's our go-to for this section of work. Okay. I'll do them as a diagram as well on the next page. First of all, at the bottom of the loop, let's just digest this. Your reaction force, I like to say it has to do two things. Your reaction force has to supply the centripetal force towards the center of the circle, and it's got to overcome the weight force as well, mg. I've put these bars here, which of course mean the absolute value. You'll see why in a moment. The next one. Now at the top of the loop, your gravity is in the same direction as your centripetal force, downwards towards the center of the circle. So now your reaction force, it still needs to provide your centripetal force, but because gravity, your weight force, is in the same direction as your centripetal force, it doesn't need to supply, your reaction force doesn't need to supply all of your centripetal force. So that's hence the minus sign there. Let's look at that graphically when we look at the next page. And before we do, please don't forget, guys, on our OneNote, we've got other resources like a PowerPoint and anything else that's relevant, like other websites and other screencasts. It's always good to get that other opinion, another explanation. Okay. Let's look at it. Actually, we will go back. My apologies. We will go back and look at the diagram and try and get some concept of that. At the top of the loop, our net force in red here needs to be yay big towards the center of the circle. Now, depending upon how fast you're going, what your mass is, and how tight the circle is, mv squared on r, that centripetal force requirement might be big, small, or whatever. It varies. But certainly one thing that won't vary is I'll make it small to start with. Your weight force is going to be supplying some or maybe all of your centripetal force. So what that means in this scenario, your reaction force, I'll call it FR, not resultant but reaction. Actually, sorry guys, let me just double check. Have we used FR? Yeah, FR for reaction. We could use N for normal if we wanted to. Okay, so in this scenario that I've just drawn, your reaction force is only going to be quite small. It's the difference between your centripetal force required in red and your weight force. While we're here, let's tweak this and let's say that we'll leave our weight force constant. If we go slower, if we go more slowly around our circle, let's say now that the centripetal force required is less. In this example, gravity supplies all of our requirements for centripetal force. So in this scenario, our reaction force becomes 0. You feel weightless. And I'll say it again, if gravity, your weight force can supply all of your centripetal force, there's no reaction force, and that's when you feel weightless. So that's like people in the space station or anything orbiting around Earth, or if the designers of a roller coaster get it just right, so you feel weightless at the top of the circle, at the top of the roller coaster. Now, pause if you need to. Let's say if we go around really fast. Okay? If we go around really fast, like this, and our centripetal force is really large, what we need now is we need our reaction force to be downwards. If this person is going over the top of a roller coaster, the only thing that can provide a downwards reaction force is like a harness or like a seat belt on top of them. That's why in roller coasters you often have that bar that comes down over your head. It stops you from flying off out into space. It provides a downwards reaction force. Stops you becoming a projectile. Okay? That's 2 scenarios with this. We'll look at the third one in a minute. Okay? Let's look at down the bottom now. Down the bottom of our roller coaster, we've got this scenario. Your reaction force is going to be your centripetal force plus your weight. I'll show you why. Here's our centripetal force, always towards the center of the circle. That's our net force. Here's our weight force acting downwards. I'll put that in green. W for weight. Now, our reaction force needs to be at least as big as your weight and supply your centripetal force. You've got a massive reaction force. So you're going to feel heavier because the seat is applying a large reaction force on you. And that's how you judge, you get that feedback as to how heavy you feel, is the amount of reaction force on your body. Sitting here, just watching this, you're getting 1 Gs. Your reaction force is your weight force. It feels normal. But down the bottom of a roller coaster here, your reaction force might be twice your body weight. You feel heavy. All right, I've gone right into the guts of it there. I've really tried to explain the whole thing in one go. If you didn't understand that, go back with the screencast and take it in little chunks. Okay. On this next page is a summary. Before we get to the summary, let's look at a couple of examples and pause and digest it a little bit. Let's look at this concept of how reaction force influences how heavy you feel. Okay? Let's go through it. The reaction force is large at the bottom here of the loop. Because for the net force to be directed inwards, the centripetal requirement, the reaction force has to be greater than the outward gravity force. It's the sum of gravity, your weight force, and your centripetal. At the top of the loop, though, the gravity force, or your weight force, I should say, really, to be a little better, is directed inwards or downwards or inwards and towards the center of the circle. And thus, there's no need for a large reaction force in order to sustain the circular motion. So, note, at the sides of the loop, so we're talking about, oops, we'll go back. At the sides of the loop, we'll get there. We're talking about here and here, right? That's in the previous page. At the sides of the loop, we can ignore gravity because, well, in terms of the reaction force anyway, because it's perpendicular to that centripetal force at that instant. Okay? So your centripetal force, and let's highlight it, at the sides of the loop, the centripetal force is provided by the reaction force. Gravity can be ignored because, I'll just summarize it here, weight is perpendicular to your centripetal force. So there's no component of gravity acting inwards towards the center of your circle. It's not providing a centripetal force. All right. Now, before we do an example and before we go to these summary diagrams that I've added extra in here, pause for a moment, go to your textbook and take a moment to do task 14. It's figure 2.6.2. So in other words, it's the second diagram in section 6 of chapter 2 of your textbook. Pause for a bit and then come back and we'll do example 5. All right, so let's continue. So task 14 was figure 2.6.2. It's pretty self-explanatory. If you read the textbook, it does that quite nicely. So let's not dwell on it. Let's jump straight to example 5. Step 1, pause, read the full question, and you can pause while you read it, and then we'll come back and I'll keep working through it. So we've read the question, and obviously at which point in the circle would the string most likely have broken? It's obviously going to be at the bottom. Okay? Why? Notice it's got two, it's asking you to do two things. There's a question and then explain your answer. So obviously at the bottom because, okay, the tension is like a reaction force for a roller coaster or the lift force from the wings of an aeroplane. The tension at the bottom there will be at its greatest. That's why it's going to break. But why? Because right? The tension has to supply the centripetal force, and we're not going to worry about directions. And at the very least, it has to overcome the weight of the object as well. So at the bottom, those two vectors add vectorially to mean that the tension has to be greatest, as we'll see in the summary diagram shortly. So now, part B. What was the force required to break the string? Okay, so we start with that formula that we just used. T, and I'll just call it TB, the tension at breaking point. So, mv squared on r, it's got to supply the centripetal force, and it's got to at least overcome the weight force. Okay. Now, let's factorize for m. 30 grams, don't forget it's got to be SI units. So we'll have 0.03. And we'll factorize v squared. The velocity was 13.6 squared. The radius we noticed in the question was 75 centimeters, 0.75. Okay, and then simply plus 9.8 because we've factorized for our mass. And crunch those numbers and we get 7.69 newtons. And there's two ways we can talk about the tension, the force. Because it's a force, it needs direction. We could say towards the center of the circle, or we could say along the string, because there's only one way the tension can act in a piece of string or rope or chain. It's along the length of it. So take your pick. Towards the center of the circle or along the string. Okay? All right. Now's a good time for us to just recap, and I'll try and do this nice and slow. Okay. At the bottom of the circle, at the bottom of the loop, there is only really one scenario possible. The magnitude of these vectors might change, but their direction won't. Okay? If there's the center of mass of the object right there, the net force is our weight force plus a reaction force. And our net force has to be towards the center of the circle. Remember, kind of there's the bottom of our loop-to-loop, or the whatever the path may be. So essentially, right, our reaction force has to be, in terms of magnitude, our net force and our weight force. That's why it's really big at the bottom. You'll feel heavier. The person feels heavy. Easy. There's only one scenario there. How big that has to be? Well, that depends upon how fast they're going, mv squared on r. That depends on these variables here. But either way, it's bigger than normal. Now, at the top of the loop, you've got three possibilities. You've got one force, that's our weight force, that remains unchanged. It's the relationship between that weight force and your centripetal force that determines what your reaction is going to need to be. So, in the first instance, where your weight force isn't quite supplying your centripetal force, you need to have some sort of reaction downwards. The person feels lighter. Okay? And if that reaction force wasn't there, they would lift off and no longer be going in a circle. So if they were at the top of a roller coaster, they would leave the roller coaster and become a projectile. This is where we talk about, for a person, those big bars that come down on top of you, those padded bars, or a seat belt, or for a pilot, they need to be strapped into the seat. Something needs to push them down to make the net force your reaction plus your gravity. So for a roller coaster, that's not really a good scenario at all. People are going to die if they're not strapped in properly. Okay. Alternatively, I'll call that scenario 2 and the other one scenario 1. Scenario 2 is you might be going slower, or you might be going in a larger radius turn where your weight force is bigger than the centripetal force requirement. So your reaction force is going to be upwards. Okay? So you will still feel lighter, but you need an extra reaction force. There needs to be something that's going to push you upwards. Okay? You still feel lighter because your reaction force is smaller than your weight force, but you still feel like you're pressed up against the seat. Okay? And the reaction force needs to be upwards. You could get away with not having a seatbelt on in this scenario. If they get it just right, the third scenario here is if your weight force exactly supplies the centripetal force that you need, then your reaction force becomes 0. Okay? Your net force is still your reaction plus your weight force. It's just that that's 0 now. It's at that instant that you feel weightless. And that's what they would kind of aim for with roller coaster design. And like I said, the people that are in orbit around the Earth in the space station, they're not actually weightless. It's just that their weight of gravity is supplying the centripetal force at that time. So there's no reaction force between them and the floor of the space station or the wall or wherever. They can just float. They're falling at the same rate as the space station. Okay. Now, I think that's frozen. So what I might do is I'll stop it there. Whew, that's a big one. Take it in little chunks if you need to.